Hello everyone, I'm Resck, and I'm going to present the paper exploring the trade-off between model performance and explanation plausibility of text classifiers using human rationals. I have just finished my master's degree in mathematical modeling at Fundação Getúlio Vargas in Brazil, and this work is a collaboration with Professor Jorge Poco from Fundação Getúlio Vargas and Professor Raimundo from the State University of Campinas, both in Brazil. Let us start with an example motivation. Suppose you have a complex text classification model. The model receives a text input and outputs a prediction. And one may want to understand the model decision. For instance, they may want to know which are the most important tokens for the model decision. There are several methods to do that, such as LIME, SHAP, and integrated gradients. These methods allow us to identify the most important tokens for the model decision. Consider, for instance, these two examples of model explanations. Green means a positive contribution to the model decision, while red means a negative contribution. The intensity of the color indicates the importance of the token. We have two different explanations, but which one is better? Explanation A highlights the words great and movie, which are words that indicate a positive sentiment, while explanation B highlights the words is and such, which are not as relevant. Therefore, explanation A is more plausible, as it matches more human intuition. And ideally, the explanation would be something like great movie, as they are the most important words. This annotation on the text is what we call a human rational. Therefore, given that we know we can extract model explanations and we know what they ideally should be, how can we make the model explanations more plausible? So let's define some notation. Suppose we have a multi-class text classification task. We also have a set of classes C. We also have a model represented by G theta that outputs logits. And we have a set of texts X and labels Y. Therefore, we can use the standard cross-entropy loss. So we average over the samples, we sum over the classes, there's an indicator function for the correct label, there's a logarithm, and we use the softmax function to get the probabilities from the logits. In this work, we propose a modification to the cross-entropy loss. We call it the contrastive rationale loss, and the modifications are twofold. First, instead of the full text being the input, we use the human rationals, the annotations, and their associated labels. Second, instead of the softmax function, we use a different calculation. The numerator is the exponential of the logit of the correct rationale in the correct class, and the denominator is the sum of the exponentials of the logits in the correct class as well, but for random negative rationals. These negative rationals are randomly sampled over the original text. So we teach both the correct rationales and the wrong negative rationales to the model. Okay, so we have two losses, the classification loss and the contrastive rationale loss. And to work with both of them, we multiply each by a weight, W, and add them. We use a multi-objective optimization solver to explore the trade-off between these two losses. The solver samples weights W1 and W2 in a smarter way than simply random sampling or grid search. This allows us to explore the trade-off between the two losses, and therefore the trade-off between performance and plausibility. For the main experiments, we use the Distilbert model and the H-explained dataset. The Distilbert is a simpler version of BERT, the most popular transformer encoder. We add a classification layer and train only it. And the H-explain is a dataset of hate speech detection with human annotated rationales. We use it as a binary classification between normal and hate speech classes. The diagram exemplifies our task. The Distilbert model receives a text and outputs a prediction. In this case, the prediction is hate speech. The model receives and learns from the rationales only during training. For the results, we have two plots here. The first one shows the trade-off between the two losses on the training data, the cross-entropy loss and the contrastive rational loss. For instance, consider this model here, with cross-entropy weight W1 equal to 1. In this case, the model is trained only for classification without any explanations. As we decrease W1 and increase the contrastive rational loss weight, the contrastive loss decreases and the cross-entropy loss increases. So we see a trade-off between these two losses. And while the first plot is on the training data, the second one is on the test data. So for each model, we evaluate both the performance, measured by the accuracy, and the plausibility, measured by the metric AUPRC, which is the area under the precision recall curve. It's basically an agreement metric between the model explanation extracted with LIME and the human annotation. So, as you increase the contrastive rational loss weight, the test explanation plausibility increases. And this increase comes with a small cost of performance drop. So, on average, explanation plausibility is increasing as we increase training with rationals. But what is happening in the individual explanations? The right figure shows two explanations from the same sample, one from the original model and one from the model with the highest AUPRC, this one. We see that the original model explanation selects a token that is not as relevant, while the model with the highest plausibility selects the most relevant token, as we would expect. This figure shows the trade-offs between performance and plausibility for all models and datasets. Besides H-explain, we also have two other datasets. And besides Distilbert, we also have two other models. We have the accuracy on the x-axis and the plausibility on the y-axis. In all graphs, we see some kind of trade-off between the two metrics. For instance, in a few graphs, we see a relevant plausibility increase with a small performance drop, such as here and here. In other graphs, we see an increase in both metrics, such as here and here. Finally, in just one case, we see a relevant decrease of performance to achieve a relevant increase in plausibility, which is this case. The green dots in each graphic are models that I manually chose to represent the trade-off and compare with the original model. This table shows the comparison between the original and the chosen models. For each dataset and model, we can see the variation of accuracy and AUPRC. In all cases, we see a relevant increase in plausibility in both AUPRC and relative AUPRC variation. And with the exception of one case, which is the TF-IDF with H-explain, the performance either increases or the performance drop is small when compared to the relative AUPRC variation. The contributions of this work are threefold. First, we propose a novel contrastive-inspired loss function that effectively incorporates rationales into the learning process and is model and explainer agnostic. We develop a multi-objective framework that automatically assigns weights to the learning loss and contrastive rational loss to effectively explore the trade-off between performance and plausibility. And we perform a series of experiments using various models, datasets, and explainability methods to demonstrate a significant enhancement of model explanations without compromising the model's performance. The key takeaways of our work are: the novel contrastive inspired loss function, which is model and explainer agnostic, and a significant enhancement of model explanations. Thank you very much for your attention. Please check our paper and also our code on GitHub.